So in this video, we're going to be talking about one of the most well-known geometric proofs of the Pythagorean Theorem. So we all know that, like, well, you're going to know if you haven't learned it to this point, but if you have a triangle with a right angle here, for example, and you have side lengths of A, B, and C, and let's call this angle A is across from side A. This is angle B. Then the relationship we're talking about is a squared plus b squared equals c squared. So you may have seen this on your homework before, your teachers told you about this, but how do we know that that's actually true and it holds up? Well, take for example a square. Now let's give the square side lengths of a plus b, and because it's a square, it's going to have all right angles in there. And okay, so let's say that this part here is length A, this is B, and if you go all the way around, we're going to say that we can draw it like this. So if you start drawing your right triangles in here, then this is going to be A and B. Okay. So this is what we get, and by the way, these are all side length C. So in the construction that we've just come up with here, well, let's go ahead and put our angles in there. So this is A, and then just put in angle A all the way around like this, and then we're going to put in angle B for all of them, and of course angle C is just the right angle, so we know what that's going to be. But we know that the three angles for the interior angles of a triangle, we know that A plus B plus C equals 180 degrees for adding up the angles here, but also we know that C is the right angle. So A plus B plus 90 degrees equals 180 degrees. Subtract 90 from both sides, and we know that the quantity A plus B has to equal 90 degrees. Now, why is this important? Well, notice here that we're going to have straight angles on every single side of our square here. So notice that if we call this, like, say, angle 1, 2, 3, 4, and we want to know what those are, then I'm going to write my reasoning here. So this was right. This was triangles, interior angles to 180, but also we know that we have to have A plus B plus, for example, angle 1, and that's also going to be the same thing as A plus B plus angle 2 plus A plus B plus angle 3 plus A plus B plus A, that should be an equals, plus angle 4 equals 180 degrees. Now this relationship should be an equals. Okay, this relationship here is true, by the way, because they all sum to a straight angle is 180 degrees, but we know that the quantity A plus B is 90 degrees. So if we substitute that all in like this, then we're going to get 90 degrees plus angle 1 equals 90 degrees plus angle 2 equals 90 degrees plus angle 3 equals 90 degrees plus angle 4, which all of these equal 180 degrees, but if you subtract 90 from all of them, then what you get is that angle 1 equals angle 2 equals angle 3 equals angle 4 equals 90 degrees. In other words, inside here, we're just going to get that this is going to be a small square inside here, because it's going to have side length of C all the way around. So the area basically is going to be S squared here, because we also are guaranteed by how we constructed it to get right angles for all of these angles. So what can we do next? Well, let's go ahead and find the area. So let's say area of the big square, uppercase SQ equals the quantity A plus B squared. Just remember that's side length squared. So that equals A plus B times A plus B. And now let's go ahead and multiply this out. So we get A squared plus AB plus BA plus B squared. But notice here also that I could write this over here, AB equals BA by the commutative property of multiplication. So because of that, we can just go ahead and substitute this in here. So this is the same as saying A squared plus AB plus AB plus B squared. Then you combine the like terms, equals A squared plus 2AB plus B squared. So that's the area of the whole thing in here. But also, if you recall, we have some areas of small triangles, and we have an area of a small square in there, and the area of this triangle here is 1/2 of the base times height. Well, in here we have base B and height A, so the area of this triangle is going to be just simply 1/2 B times A, or 1/2 AB in other words. So we can also represent this area as area of the big square equals area of the 4 triangles plus area of the small square inside. I'm going to call that lowercase SQ. So this is going to be, well, actually, let's say this is 4 times the area of the triangle, because we're going to take equals 4 times our area, which is 1/2 AB plus the area of the square inside here, which the side length is C, so take C squared for our area. So that's going to be 2ab plus c squared. But notice here, these are just two ways of describing exactly the same amount of area of the entire larger square. So we can actually set these equal to each other. So a squared plus 2ab plus b squared equals 2ab plus c squared. And we can cancel these out by subtracting 2ab from both of them. And we get a squared plus b squared equals c squared. So therefore, the Pythagorean theorem holds. Okay, so this is just a common way to prove it with a square. Proving it with if you wanted to prove it with a trapezoid, that's not that much harder to do. Basically, a common way you could do that is you could just draw kind of like a line in between here, and then the trapezoid ends up being half of the square, and then basically it's the same kind of thing, but you're just going to have half as much area to deal with, so you just multiply everything by 2 in the end. I can do a different video about that, but yeah, hopefully you found this helpful and it was insightful. So yeah, come back for the next one where Joe shows you how.